Okay, I am Mr. Baker, and we're going to go over the midterm review for on-level Physics 1. We're going to do these one at a time. So this is the first one for kinematics. All right, so we're just going to talk about a few things with this graph because they're things that we need to know. So when we're talking about any graph, we're concerned about the slope. The slope of this graph, the slope of a position versus time graph, is velocity. That's an important thing for this. So if we have a position versus time graph that looks like this, that's positive slope, and that slope does not change, so that means we have positive constant velocity. And since the velocity isn't changing, since it's constant, we're going to say that the acceleration is 0. If we have a position versus time graph that looks like that, we have a negative slope that doesn't change. So that means we have a negative velocity that doesn't change, or we have negative constant velocity. And since the velocity is not changing, we're going to say that the acceleration is also equal to 0, just like before. So if we see a straight line on a position versus time graph, that means constant velocity and 0 acceleration. Now, if the slope changes, that means we have a curved line. The line curves, and that means if the velocity changes, the line curves as well. Anytime we see a curved line on position versus time, we're going to have an acceleration. So if the line curves, the object has to accelerate. So those are the things that we're looking at for a position versus time graph in general. So we're gonna answer each part of this. Which object is accelerating at time equals 1 second? So if we're looking at the object that's accelerating, we're looking for the curved graph. That's object C that has a curved graph. So object C is accelerating at 1 second. Find the velocity of all three objects at t equals 5 seconds. Well, t equals 5 seconds is the very end of this thing. So if I'm going to find the velocity, I'm going to need the slope of each object at t equals 5 seconds. So we're going to find, you might want to write that down. Find the slopes at t equals 5 seconds. So if we look at object C, the slope for object C is 0. If we look at object A, the velocity is the slope. That's the change in position over time. So if we look at these 2 points, this point and this point, it's the change in position. So that's 2 meters divided by the time of 4 seconds. So that speed is half of a meter per second. We do the same thing for line B, that velocity is change in position over time. So what we're going to do is look at this change in position and this change in time. It's going to be -1 divided by 4, so that velocity is -0.25. So velocity at 5 seconds for A is half a meter per second. Velocity at 5 seconds for B is -0.25 meters per second. And at C, the velocity at 5 seconds is 0. All from the slopes. At what time do A and B have the same position? That's going to be when their graphs, when those lines cross. So let's write that down. They have the same position when the lines intersect. So when the lines intersect, they have the same position. That's 2.5 seconds. How far from the origin is object A after 20 seconds? Now this graph only goes to 5 seconds, so we're going to have to look at what's going on with that. We're going to have to look at the equation for the motion. The equation for this motion is x is equal to x initial plus velocity times time. That's just y equals mx plus b. I'm just substituting its values there. So for object A, the initial position is 2 meters. The slope we found was half of a meter per second. We're going to multiply that by 20 seconds. So we'll put that all in the calculator. That gives me 12 meters. We're going to do the same thing for object B, but we want to find out when it reaches the origin. So we're going to use the same equation, position equals initial position plus velocity times time. My final position is 0. My initial position is 4 meters. I get that from the graph for object B. And that's plus the velocity, negative 0.25 meters per second, times the time. So I'm going to take that equation and solve it for the time. So I'm going to subtract 4 over for both sides. That gives me negative 4 equals negative 0.25 t. I'm going to divide both sides by 0.25. That gives me a time of 16 seconds. So, for object C, the initial velocity is 0 and the acceleration is constant. I want to find the acceleration of that object. So to do that, we're going to have to use our kinematic equations, and we're going to have to write down our knowns and our unknowns to figure it out. Ooh. Sorry about that. We have to write down our knowns and our unknowns to figure it out. So, the initial velocity is 0, it tells me that. The time is 2 seconds, and the change in position is 2 meters. I get all of that from the graph. Most of that is from the graph, right? I can read that from the graph. And so what I want to find with those things is the acceleration. The acceleration we don't know. So the kinematic equation that has all of those variables in it is the delta x equals v initial times time plus 1/2 acceleration times time squared. So what's really nice about this is that the initial velocity is 0. So that bit goes away. So that gives me delta x is equal to 1/2 at squared. We're going to plug in our number, so we're going to solve for the acceleration. We're going to multiply both sides by 2. That gets rid of the 1/2. We're going to divide both sides by t squared. That gets rid of the t squared. So the acceleration is all by itself. So we're going to copy the left side of that down. 2 delta x over t squared is equal to the acceleration. So 2 times 2 divided by 2 squared is the acceleration. Put that into your calculator and you just get 1 meter per second squared. All right, the next part, we're going to look at these graphs and we're going to determine which object, all these questions. So part A wants to know which object is accelerating. Well, like we said before, the slope equals acceleration. We talked about a position versus time graph. I apologize. Let's talk about a velocity versus time graph. For a velocity versus time graph, the slope is acceleration and the area is the change in position. That's the next bit of information we need to know. So if I want to know which objects are accelerating, if I look at the position versus time graph, graph A, I want to see a curved line for acceleration. I definitely see that for graph A. For graph B, I see I have a negative slope. That means I have a negative acceleration. So that one's accelerating as well. And graph C is just a graph of acceleration versus time. That shows me that I have a constant acceleration of positive 2 meters per second squared. That one's accelerating as well. They're all accelerating. Which objects have negative initial velocity? Well, the slope of graph A, because it's a position versus time graph, is velocity. That starts off with the slope of 0. In object B, for object B, the initial velocity is positive, and we don't know the initial velocity for object C. So none of those have an initial velocity. Which objects have a negative acceleration? For object A, the slope goes from 0 to positive, which means the velocity goes from 0 to positive, which means the acceleration is positive. Graph B is velocity versus time. So the slope is acceleration. That has a negative slope, so it has a negative acceleration. So object B definitely has a negative acceleration. Object C has a positive acceleration. It says that the acceleration is 2 meters per second squared. And then for D, which object has a negative initial position? Object A shows me position. That's the only one I can get information about position from. I don't know what the initial position is for objects B and C. So looking at it now, A has initial position. We don't know. I'm sorry, A has a positive initial position. We don't know the initial position for the other ones. Okay. 3, an object starts at rest and then moves with a constant acceleration of 2.5 meters per second squared. This is a question that's going to have us use the kinematic equations. So to do that, we're going to write down all of our knowns, pick our unknown, and then choose a kinematic equation to help us solve the problem. So for part A, I want to know how far it's moved from the starting position after 25 seconds. So the acceleration is a constant 2.5 meters per second squared. It's given in the thing. The initial velocity is 0 because it starts at rest. And then the time is 25 seconds. What I want to know is how far. That's delta x. That's my unknown. That's what I'm after. So I want an equation that has all of those things in it. That's the delta x equals v0t plus 1/2 at squared equation. That whole v0t, v initial times time term goes away because the initial velocity is 0. So that leaves me with the equation delta x equals 1/2 at squared. So it's 1/2 times the acceleration of 2.5 times the time of 25 seconds squared. We put that in our calculators and we get 781 meters. Part B, how long does it take for the object to reach a velocity of 24 meters per second? For our knowns, we still know that the acceleration is 2.5 meters per second. We still know that the initial velocity is 0, but now we know that the final velocity is 24 meters per second, and we want to find the time. So the equation that has all 4 of those things in there is the final velocity equals initial velocity plus acceleration times time. Because the final velocity is 0, that thing crosses out. And so I get final velocity equals acceleration times time. So I'm going to go ahead and plug in my numbers. 24 is equal to the acceleration, 2.5 meters per second squared, times time. I'm solving for time, so I want it on top and by itself. It's already on top. So I'm going to divide by 2.5 to get time all alone. So 2.5, both sides get divided by that. Crosses out on the right. And so that time comes out to be 24 divided by 2.5, or 9.6 seconds. The next part is how far does the object go before it has a velocity of 24 meters per second? So again, we're going to write down all of our knowns. The acceleration is 2.5 meters per second squared. The initial velocity is 0. The final velocity is 24 meters per second. The time we just found to be 9.6 seconds. And the displacement is what we're after. So we have a couple of different options. That's all 5 things that I could possibly know. So I could use any equation that has delta x in it, any equation that has displacement in it. So that displacement, I could use displacement equals v initial times time plus 1/2 at squared. Because the initial velocity is 0, that term goes away. So displacement is equal to 1/2 times 2.5 times 9.6 seconds squared. That displacement comes out to be 115.2 meters. Or we could do it another way. We could pick another equation. The other equation that we use, I'll give myself a little bit of room here. The other equation that we could use is the other one with the displacement in it. Final velocity squared equals initial velocity squared plus 2a times the displacement. The initial velocity goes away because it's 0. So v final squared equals 2a times the displacement. So we're going to plug in all of our numbers. 24 squared is equal to 2 times 2.5 times delta x. We want to isolate delta x. We want to get it all by itself. So we're going to divide both sides by 2 times 2.5. That's going to get rid of it. So that's gone on the right side, and I've got on the left side 24 squared divided by the quantity 2 times 2.5. So 24 squared divided by 5. We put that in our calculator, and we still end up with 115.2 meters. All right, here we have a velocity versus time graph, and we want to answer these questions with it. So for velocity versus time, some things to keep in mind. The slope of this graph is acceleration. That's really helpful. And the slope in general is y2 minus y1 over x2 minus x1, if we need to find the slope at any point. Positive slope here, because the slope is acceleration, is positive acceleration, and negative slope is negative acceleration. So, question A asks, what is the object's initial velocity? Well, if this is a velocity graph, and I want the initial velocity, that's going to be the velocity at time equals 0. Well, I can read that straight from the graph. The v initial here is going to be 2 meters per second. What is the acceleration of the object at 3 seconds? The acceleration is going to be the slope at 3 seconds. So if we look at 3 seconds, I want the slope of that entire line. So that's the y2, negative 2, minus y1, positive 2, over x2, 4, minus x1, minus x1, 2. So that gives me negative 4 over 2, or the slope there is negative 2 meters per second squared. What's the acceleration of the object at t equals 5 seconds? Again, it's going to be the slope at 5 seconds. So if we look at 5 seconds, where that red dot is, I see that the slope is 0. So the acceleration must be 0. What's the acceleration of the object at 10 seconds? Well, to get that, I need the slope of the entire line. The slope at 10 seconds. So to get that, I'm going to get the slope of that whole line. I'm going to take the final velocity, 1 meter per second, subtract the initial velocity for that segment, which is negative 2 meters per second, and divide it by the whole time for that segment. So that's 12 seconds minus 6 seconds. That would be the slope of that line. So I get 3 over 6, or half a meter per second squared. At what times is the object at rest? So being at rest happens when the velocity is equal to 0. That's going to happen when the line crosses the time axis. So if we look at that, I cross the time axis at 3 seconds and I cross the time axis at 10 seconds. So this object is at rest at 3 seconds and 10 seconds. How far from its starting position is the object after 2 seconds? What we want to do is find the area at 2 seconds. So at 2 seconds, it's just that little square. The area of that square is 2 times 2. So the area at 2 seconds, delta x is going to be 2 meters per second times 2 seconds, giving me 4 meters. Continuing with question 5. A ball is dropped from the top of a building that's 15 meters tall. Find the time needed for the ball to reach the ground. We're going to write down our knowns. Since it's dropped, the initial velocity is 0. It's falling 15 meters, so the delta x is 15 meters. And because it's in free fall, this is important, the acceleration is 10 meters per second squared down. I want to know the time it takes for all of that stuff to happen. So I want the equation that has all 4 of those things in it. That equation is delta x equals v0t plus 1/2 at squared. Again, the initial velocity is 0, so that goes away. And so I'm going to plug everything in. 15 is equal to 1/2 times 10 times t squared. So what I want to do to solve for time is to get time on top and by itself. It's already on top. So the first thing I need to do is multiply both sides by 2. That's going to get rid of the 1/2. Then divide both sides by 10. That leaves me t squared is equal to 2 times 15 divided by 10. Or 3 is equal to t squared. So we'll take the square root of 3. And that time is 1.73 seconds. Determine the velocity of the ball just before it hits the ground. All these same things are true. The initial velocity is 0. The acceleration is 10 meters per second squared. The displacement is 15 meters. And I want to know the final velocity. The equation that has all 4 of those things in it is velocity squared equals initial velocity squared plus 2a delta x. I'm looking for that final velocity. The initial velocity is 0, so that final velocity is the square root, because I want to get rid of the square, of 2 times 10 times 15. Put that into our calculator, and the final velocity is the square root of 300, or 17.3 meters per second. So what we're going to do is take that information and graph it on the axes below. So for position, I know that we're accelerating, so that's going to need to be a curved line. But my position starts off at 15 meters. My final position is on the ground at 0 meters, so my delta x is 15 meters. And I know my acceleration is 10 meters per second squared down. My line has to curve because it accelerates, because my velocity changes and my slope changes. So if we start off at 15 meters, end up on the ground, and curve, it's going to curve down like this. Start off at 15 meters, end at 1.73 seconds. We're going to do the same thing for velocity. Here I know that my initial velocity is 0. My acceleration is 10 meters per second squared down. My final velocity is 17.3 meters per second down. So I'm starting off with a 0 velocity, ending with a negative velocity, and I have a constant negative slope the whole time. So looking at 6 and 7, second, sorry about that. So looking at 6, this picture shows the motion of an object at equal time intervals. What can we say about the motion of this object? Well, if we look at that, the object is moving less distance in every second. In every little time interval, we're moving less and less distance. That means I'm not going as far each second, or my position per second, my position per time is getting smaller. It means my velocity is decreasing. The object slows down. The velocity is decreasing. For 7, we're looking at a velocity versus time graph. We know that we have positive slope, so we have positive acceleration. I see that the initial velocity is 0. I'm sorry, the initial velocity is negative. That's all we're after there.